This video is part one of a series that I'm going to create for how to do engineering calculations for mold design. This particular series is for cooling or cooling considerations. The first thing that I do when I'm starting off, once I've got my mold basic layout done and I'm getting ready to design the cooling system, is I go to molding calculations, chiller sizing, and that's where you'll find the information that we're looking for this particular video. The part weight can be chosen in several different units, and generally we deal with grams both when specifying the part weight for mold design and for the hot runner purchase. I'm going to work in Fahrenheit for temperature units because that's what we do here in the States, and I'm going to choose a part weight of 3 grams to start with. It's kind of a typical part weight for the kind of molds that I generally design, and we'll say it's a 64 cavity mold with a 10-second cycle time, and there'll be no hot runner, no runner, because it's full hot runner, so there'll be no runner weight in this particular case. For a hot cold combination, you can enter the runner weight in here, and for a cold runner you can also absolutely enter the runner weight. Next, we choose the material, and this is more accurate if you use the specific heat for the exact grade of material that you're going to use, but for general purpose calculations, just getting started, I usually just use these generic ones that I've supplied within the software. And in this case, we're going to look at a polypropylene homopolymer, and I'll leave that open so you can look at that if you want to. The melt temperature for this material is generally around 450 degrees. And we'll say an ejected part temperature of 170 with a allowable rise in the coolant temperature from one end of the mold to the other of 2 degrees. So we keep it very uniform across the entire mold. And then there's a space there for factor of safety. You don't have to put anything in there. Usually it's between 1.2 just for miscellaneous heat loss, and I'll put 1.2 in this particular case. I'm not going to concern myself with the heat from the hot runner at this point because I'm only concerned with the mold design itself. Molders certainly would want to do that, and you allow that as a percentage, as a whole number for the entire mold. You could say 30%, to remove the heat from the hot runner, but in this case I'm going to leave it blank. When I hit calculate, you'll see that it tells you that you will process 152 pounds of material per hour, or about 69 kilograms per hour. You need to remove over 28,000 BTUs, or over 8 kilowatts of heat. You need to supply 34 gallons per minute of water, or roughly 129 liters per minute, and also the required chiller capacity is there if you're sizing a chiller for this particular project. I use this information later on for other things, but like pressure losses and such. But just to give you a feel for how much water is going to be required, or coolant is going to be required. Now, even when you're heating a mold with water, it's still coolant relative to the plastics. You may be heating the mold to 150 degrees, 160 degrees, but relative to the plastic, it's still cooling. It's not heating. It's heating the steel, but you still have to cool the plastic. In the next video, I'm going to look at a row of 8, say in the same 64 cavity mold. The cavities would usually be laid out in an 8x8 pattern. So we'll look at 8 in a row, and then the video after that we'll look at 1, and I'll explain why then.